Well, my springs and things have arrived, curiously enough, from a company called springsandthings.me.uk, also available on eBay at First Compression. Just do a search for long compression springs and they'll show up. So I've got the main spring here, which is pretty stiff, and the return spring here, which is a lot softer. The company that supplies these do give you a lot of technical information, basically the inside, outside diameters, the type of material, carbon or stainless steel, number of coils per centimetre and all that kind of stuff. But importantly, they also give you the rate, which is in a roundabout way basically the Young's modulus or spring constant of this thing, basically the stress strain. And this is probably a bit confusing to some people because it's given in newtons per millimetre per centimetre. So translating this, basically it's the amount of force you need to squash it by 10%, because it's millimetres by centimetres, so 1/10. And this spring is actually this one up here, which is 118 newtons, so about 11-12 kilograms for every 10% I squash it. And the way this actually works is it's irrelevant how long the spring is. What's important is that percentage. So if you imagine just a single piece of the spring and you apply a force to it, that clearly is going to close up by some percentage. Well, if you have a lot of these all in series, then when you apply the force, that force is actually transmitted to every single coil, and it's only when you reach the end stop that it stops passing that force on, equal and opposite forces and so on. So it doesn't actually matter how much force you apply, the compression is always the same percentage. It doesn't matter what the length of the spring is. So on this, I calculate that I'm going to have about 40 millimetres of squash. So if this was 160 millimetres long, then basically that's going to squash by 25%. That will be the amount of compression. And obviously 25%, if it's about 12 kilograms for 10%, then I'm looking at about 30 kilograms. If I was to shorten this to 120, then it's a third. So now it's 33%. Obviously if it's 12-ish kilograms for 10%, then I've got 3 1/3 multiplied by that, so about 40 kilograms. If I was to shorten this to 80 millimeters, clearly now my compression is 50%, so it would be 5 times this value, so I'd be about 60 kilograms. So basically by shortening or lengthening the spring, I can control how much force I need to compress it, because I'm always compressing it by 40 millimeters, it's just a different percentage. So that's the theory. We'll see if it works in practice. Right, I thought the first part I'd have a go at making, because it's possibly one of the hardest, is the end cap. And the reason that's going to be tricky is it needs to be steel, even though it's only mild steel, and I need to cut a thread on it. The internal diameter of this tube is 22 mil, and that just happens to be the same size as a tapping drill for a 1-inch UNC. So basically this is going to be 1 inch internal on the thread, and I've got a tungsten die which should do the job. Because it's a split die, I can open it up slightly to start the thread, and there's also a taper on one side. It's flush on the other, so I can tighten it up and cut with the other side just to get down to the end of the thread. But even so, I'm not going to be able to get right the way to the end stop, so I'll need a slight undercut at either end, which shouldn't be too hard to do. I'm going to trim this down to a little bit less than an inch, probably about 24.5 millimeters. So I've got 0.5 mil, 500 micron clearance on either side, and then we'll put a little bit of a taper on the start just to get this thing going. I can always face that off if necessary. So with a bit of luck, this should work, but I don't normally cut threads this size. I could do it on the lathe with a tool to get in there, a threading tool, but since I've got this, we'll give it a go and see if we can't make a little end piece. Right, this is the setup on the lathe. I'm using a fixed steady, and I've just faced this end off. It doesn't need to be enormously accurate, and all I'm going to do is come in and mark where I want this. So probably something like, I don't know, go in 20 mil, maybe a bit less than that. Well, we'll call it 20, we can tidy it up afterwards. So I'll just plug in and just want to score this. Myself a mark there, and then mark that at 16. So the front section is going to be where the thread is, and I'll put a taper on the front, and then between those two score marks I'm just going to need that little bit of an undercut once I've cut it, but I'll probably remark that anyway. So let's get started. Okay, let's see where we're at. So that's 25 1/4, so a little bit more off that, and that should be okay. Okay, let's see where we are. 24.5956, so maybe just a little fraction. Right, okay, that'll do for the main thread part. I now want a taper on the front here and an undercut in this portion here. So I'll just rearrange this and we'll do that quickly. Okay, we'll have a go at putting a little bit of a taper on this end. That down. It's about 15-degree taper. Okay, that should do it. Well, due to an unfortunate problem with the lighting, I can't really see what I'm doing. So, just to demo it, I'm basically coming in with a nice sharp pointy tip to take this undercut down, and then I can swing this around and take it out on the other side, but I don't think I need to, because if I get the angle right, the rake on the bit, well, after a lot of messing around, I finally got the undercut done. It's a bit rough and ready, but I should be able to cut a thread on there and part it off at about here with the chop saw, tidy it up a bit, and that hopefully will do for the top bung, and then I'll do the rest. Right, well, I've got this in the pipe jaws of the vise, good and tight. A little bit of cutting fluid around everywhere, and we'll get this started. See if I can get that on straight, will help. Okay, and we're off. It's certainly not easy, but it's doing it. And I think I'm all the way at the bottom. Yep, certainly looks like it. So now I'll get this the right way up, and that's the side without the taper. So if I just run it down with this, should be able to get that last part of the thread tidied up. Well, to be honest, it's not looking too bad. It's cut reasonably cleanly. Seems to be a reasonably good match for the end stop that I'm looking for, and since I've already done a second one here, I think I'll probably use that as the end stop, and I'll use this one for the other end. So that one will go there-ish, and I'll chop this off down here and just maybe put a little bit of a taper and tidy it up. So time to make a few sparks with the chop saw, I think. Right, well, this is where we hope we don't set fire to anything. It's still a little bit toasty, but it's cut off quite nice and neat. It's still very warm, in fact. So next stage is just to tidy this up, maybe put a little bit of a taper on it, drill it through when I decide what size plunger I'm going to have on this, and the rest of it's fairly straightforward. This bit here I think I'll cut out of that again, just thread it down with a die, and then bore out the insides afterwards, because otherwise it's going to get a bit thin at this section. So we'll do it thread first and then bore second, and then the aluminium tube should be an awful lot easier to cut than this stuff is.